paper titled Time-MoE Billion Scale Time Series Forecasting Foundational Models with a Mixture of Experts. This work introduces a novel approach to time series forecasting, addressing key limitations of existing models in terms of scalability, efficiency, and generalizability. We'll explore how the Time-MoE leverages a sparse mixture of experts designed to achieve a state-of-the-art performance. Now, the abstract, the challenge, and our solution. Deep learning has made a significant stride in the time series forecasting, but large scale pre training, common in language and vision, has been limited by high cost and scalability issues in the time capable forecasting foundational models, while simultaneously reducing inference cost. By using a sparse mixture of experts designs, Time-MoE activates only a subset of networks for each prediction, significantly enhancing computational efficiency while maintaining high model capacity. This allows for effective scaling without a professional increase in the inference cost. Time-MoE is a family of a decoder only transformer model that operates auto-regressively, supporting flexible forecasting horizons and varying input context lengths. The models were pre-trained on a new large-scale dataset. This allows for effective scaling with the proportional increase in inference cost. Is a family of a decoder-only transformer models that operates auto-regressively, supporting flexible forecasting horizon and varying input context lengths. For the first time, a time series foundational model was scaled up to 2.4 billion parameters, achieving significantly improved forecasting precision. The results validate the applicability of scaling laws in time series forecasting and demonstrated Time-MoE consistently outperforms dense models with similar activated parameters or computational budget. Now, the introduction. Why Time-MoE? Time series data is ambiguities driving critical applications across various sectors like energy, finance, and healthcare. However, the analyzing this data is challenging due to its inherent complexity and distribution shifts, yet it is a crucial for unblocking insights that enhances predictive analytics and decision making. While traditional methods and even recent foundational models have shown promise, they often fall short in terms of scale, generalizability, and computational efficiency. Traditional forecasting has been performed in a task specific end to end manner using either statistical or deep learning models. Although promising foundational models are generally small in scale and have limited task solving capabilities compared to domain specific models, limiting their real world impact when balancing forecasting precision against computational budget. Most existing time series models are dense, meaning every input token requires computational across all model parameters, leading to high computational intensity. Furthermore, many current foundation models lack flexibility in handling arbitrary context length for forecasting horizons. Time-MoE directly address these challenges by introducing a sparse MoE based architecture that allows for scaling up model with a fixed inference budget, offering a superior performance and flexibility. This work already also introduces Time 300 billion, the largest open access time series data collection, enabling the training of these massive models. Now, let's discuss upon the performance overview, outperforming the state of the art. Let's see the figure which provides a compelling performance overview. The left panel time against the state of the art time series model, reporting an average zero shot performance across 6 benchmark datasets. You can see Time-MoE consistently achieves superior results. For instance, the table shows that at 10 million activated parameters, Time-MoE achieves an average of MSE of 0.31 with 100 million activated parameters, and an average of MSE of 0.32 with 300 million activated parameters, and an average of 0.28 and with 1000 million activated parameters. An average MSE of 0.25, significantly lower than the models with a fewer activated parameters. We have other more highlights on the efficiency of Time-MoE by comparing its few and zero shot performance against a dense variants with similar effective FLOPs per time series tokens across the same 6 benchmarks. Here, Time-MoE demonstrates a better performance in both zero shot and few shot scenarios, indicating its computational efficiency and the superior predictive capabilities even under constrained computational budget. For example, 0.27 GFLOPS per time point prediction MoE time achieves a average of MSE of 0.25 in zero shot outperforming dense models at 0.28 GF ELOPS with a average MSE of 0.27. Now moving on to the architecture. The figure illustrates the elegant architecture of a Time-MoE, a decoder-only model. This process begins with the input time series of arbitrary length. This step is first tokenized into a sequence of data points, which are then encoded, and these tokens are fed into an n-stacked backbone layer. The core of these layers consists of casual multi-head self-attention mechanism and sparse temporal mixed of expert layers. During training, Time-MoE optimizes forecasting heads at the multiple resolutions. This multi-resolution approach allows for a more robust and flexible forecasting. For more model inference, Time-MoE provides a forecast of a flexible length by dynamically scheduling these heads. These modular design is a key to its scalability and efficiency. Now moving on to the methodology. Uh, Moving on to the model training and the loss function, the Time-MoE models are pre-trained on a massive time 300 billion datasets. A crucial aspect of Time-MoE models is managing the routing of tokens to experts. The training process involves optimizing not only the expert network but also the gating mechanism that determines which expert process which tokens. The loss function typically includes a standard forecasting loss such as mean squared error and combined with auxiliary loss to encourage a balanced expert utilization. This auxiliary loss prevents a few experts from becoming overload while others remain underutilized, ensuring that benefits of MOE architectures are fully realized. Multi-resolution forecasting heads are optimized during a training to enhance the model's ability to predict across different time scales. Now moving on to the main results, the zero shot forecasting. Now let's examine the main result starting with the zero shot forecasting. Zero shot forecasting is a critical measure of a model generalization ability, and it evaluates performance on unseen dataset without any task specific fine tuning. Time-MoE demonstrates a remarkable zero shot capabilities consisting outperform existing state of the art time series model. As in the uh, loss function, MoE model has achieved significantly lower average mean squared error across six diverse benchmark datasets. This indicates that the large-scale pre-training time 300 billion combined with an efficient MoE architecture enables that model to learn highly generalization representation of time series data, making it effective even in novel scenarios. Now, beyond the zero shot, also excels in distribution forecasting, where models are evaluated on datasets similar to their training distribution. The paper reports an average reduction of 24% in forecasting errors in the distribution scenarios. This further solidifies this model's superior predictive power. Let's also consider another another analysis which on upon the scalability, and that compares the training and inference and cost of a dense and sparse model. It highlights the how Time-MoE sparse activation significantly reduces inference cost compared to uh, dense models, and the right next panel has the average MSE of a 96 horizon forecasting across six benchmarks. Comparing Time-MoE and dense models, both trained from scratch with varying data size, this demonstrates that Time-MoE maintains the performance advantages even when the trained with the different data scales and showcasing its robust scalability and efficiency. Next, in the conclusion, Time-MoE paper presents a significant leap forward in the time series forecasting by introducing the scalable, unified, and efficient mixture of expert architectures. Time-MoE addresses the long-standing challenges of building large-scale time series foundational models. This creation of a time 300 billion dataset further enables the advancements. The results unequivocally demonstrate that the scaling laws applies to time series and that sparse MoE models can achieve unprecedented forecasting precision while maintaining computational efficiency. Time-MoE superiors the zero shot and in distribution performance, coupled with its flexibility in handling various forecasting horizon and context lens, position it as a powerful tool for the future research and application in the time series analysis. And this work paves the way of a new generation of highly capable and efficient time series foundational models. Thank you.